And switching gears just a little bit, we are going to talk about some different attacks that we can use in networks, or I'm sorry, in applications. Sorry. So we're going to talk about specific application attacks. And once again, a lot of these attacks are things that have been around for quite some time, but it's good to see what some of these techniques are that attackers have used over the years. And also many of these, I should say, are still perfectly valid and are still used regularly. For example, the first one we're going to talk about is cross-site scripting attacks. These are extremely common. They still happen all the time, and it's something we definitely need to protect ourselves against. And it's good to understand how they work and how attackers use these different techniques. So basically, a cross-site scripting attack is where an attacker submits code to a server, which then executes the code. There are two types of these attacks. One is called the reflected attack, which is typically delivered via email or clickbait. And the other one is a persistent attack, which is where the attacker's code is saved and displayed to all users. So I'll explain how this works. Basically, when you think about how the internet works, it's all just, things like HTML and JavaScript and so forth and so on. So your web browser goes out to a web server, gets the code, pulls it back down, and executes that code. Maybe not executes, but parses that code and carries out those instructions. Now, those instructions could be how to display a web page using HTML and CSS, for example. Those instructions could also be some basic programming code like JavaScript, or even some other scripting languages like ActiveX, which really isn't used much anymore, but it's still out there. Or it could be a Java applet, and it runs some Java applet on the client side. So the way a cross-site scripting attack works is the idea is that we're trying to get our own code to be sent to a client from a server. So we're kind of an independent, third party out in left field, and we want to get our code to execute in the web browser of a user of a website that we have no control over and we don't own. The two ways to do that are reflected and persistent attacks. So a reflected attack is basically when we send a URL to a user, and when they click on that URL, they go to a web page, but there is something encoded in that URL that gets executed by the server, and then the server then reflects information back to the user, and that's a type of attack. So I could construct, for example, a URL that says google.com Q equals Wales. And when you click on that URL, it's going to take you to Google, but not just Google, it's going to be Google with a search engine result page for a search for whales. And that's not necessarily, a bad thing, right? That's, that whole concept of embedding information in the URL, which is processed by the web server, is sort of the cornerstone of technologies like representational state transfer, or REST, which is a pretty common technique for web services. It's simple, it's easy to implement, and you can see that if you just have to put things in the URL, it's easy to construct that type of API call. But it can also be taken advantage of by attackers, those reflected type attacks. And again, and you can see on my slide that the common technique for that is things like email and clickbait, where we're embedding things in the URL. So, for example, I could send somebody a Google, URL for Google for my company or my product in an advertisement or something like that, which arguably isn't really an attack, but just, as an example, I could send something like that. A persistent attack is where the code is persistently displayed to all users on that website. So a reflected attack isn't really affecting the website, the owner of the website. So if I have a website and somebody happens to be submitting information in a URL that gets reflected to a user, it's not really affecting the code on my website. All of my users are not seeing that attack. Only the users that have that particular URL, which should be a small subset of my users. And, there's not really much that I have to do to, for that type of attack. If I want to stop it from happening, I just have to change some code maybe to not handle that parameter in a URL like that. However, a persistent attack will actually cause changes in how the website is displayed for all users. So when you see these attacks that are website defacement attacks, in many cases, those are being carried out using cross-site scripting techniques. So, thinking back to this concept of code being executed on the client like JavaScript, what if I could write some JavaScript code and somehow submit that to a website so that it gets so that it's now part of that website, so that all users are now executing that JavaScript code. And that's essentially how a persistent attack would work. So take something, for example, like Facebook. In Facebook, if I wanted to attack all of my friends, what if I could write some JavaScript that does something bad on their computer, and I write the JavaScript and post it as an update on my Facebook page? And if Facebook was not very sophisticated, and of course Facebook is extremely sophisticated and would immediately detect this type of attack, but let's just assume for a moment that Facebook was not a very sophisticated product, they would simply store that code as an update on my wall, and when somebody goes and looks at their Facebook feed, their web browser is going to see that code and execute it without really anyone's consent. So, so that's basically how that type of attack could work. Now, of course, like I said, Facebook is pretty sophisticated, and they don't, they don't usually, or they're not usually susceptible to that type of attack. But less sophisticated websites certainly could be. So a lot of these smaller websites that are developed by relatively new web developers and things like that, they're going to be susceptible to these types of attacks, and it's important to be aware that they exist and make sure that you can test against these. One great way to learn about cross-site scripting attacks, Google has a tutorial that you can go through, and I believe I have it in Blackboard. There's a tutorial in Google that shows you how cross-site scripting attacks work, and they have some exercises where you can actually try some of these different techniques and you can see them work. So it's kind of neat, so you can try that. How do you prevent these types of attacks? I mean, the best thing to do is sanitize all web input, and really a lot of these different types of attacks I'm going to talk about, you can prevent them by sanitizing input. One of the ways that attackers can get into our programs and applications is by submitting information to them, whether it's a website, a program, or what have you. So sanitizing input is probably the best thing, and it's always a cat and mouse game, this sanitizing input. There's all these different types of attacks I'm going to talk about, and you have to sanitize input for all of them, and it can be rather overwhelming, but there are lots of libraries out there that can help you do that, and there are certainly tools that can test for a lot of these different cross-site scripting attacks. If you want to try this yourself, Insecure Labs has a nice tutorial that you can look at to do this, and also I mentioned Google has one as well. So another type of attack on applications are injection attacks. There's a couple different types of injection attacks, so I'll talk about a few of these. So there are 4 types. There are SQL injection attacks, LDAP injection, XML injection, and directory traversal attacks that are injection attacks. So a lot of these attacks require that you know a little bit about these different standards and protocols. So hopefully you've had other classes where you learn things like SQL, which is a database language. So that's a structured query language used in things like Oracle, Microsoft, PostgreSQL, MySQL, and so forth, and even all of the Hadoop and things like that. So SQL is a pretty common language. You can be probably pretty rest assured that most websites that have a database backend, regardless of what it is, probably uses some form of SQL. Some syntax of SQL, which is very similar across many of the different database engines. LDAP is used for authentication in many networks. It works with Active Directory. So Active Directory has an LDAP service that it exposes. So it's great for cross-platform integration for sign-on. We're going to talk more about LDAP in this class. It's an important part of IT security is authentication. So we'll talk about that in more detail. But there are attacks for that protocol. XML, which is the extensible markup language, again, another very common protocol. It's used in the web. It's used for all kinds of applications, but we can inject things in there to try to attack systems. And then directory traversal, which I'll talk about very briefly. So let's talk about these. Let me show you some examples. So let's say you have a database that you want to attack, and it's in a website, for example, right? So let's say it's a website, and you know that when you fill out a form, so let's say there's a form on a website where you put in your email address, right? And you know that when you put that email address in, it's probably getting inserted to some table somewhere in a database. And maybe through some reconnaissance as an attacker, you've somehow figured out what the table name is. And one technique you could use to figure that out is you could try submitting bad information to the website to see if you get error messages that come back in the browser that give you some clue as to these different pieces of information. But somehow we've done some reconnaissance to figure that out. So if we know what the field names are and we know what the table names are and things like that, now we know what those SQL commands would look like. But the question is, how do I inject that SQL command in? So if I were writing some code on that web page, let's say this is just PHP code. I know that in PHP, there's going to be a variable and it's just going to be, they're going to construct a string using that variable. So there might be some code that says select data from table where email input equals, and then whatever the variable name is that it captures from the form input in my web page. So if I were an attacker, I know that if I put in user at email, it's going to insert that record into the table like so. So if I put in hacker at programmerinterview.com, it's going to insert, maybe it's selecting from a table somewhere for that value. Now, if I'm the attacker and I'm trying to figure out if they're protecting against this type of attack, notice what I did at the end of that SQL statement. So for those of you that took a SQL class or a few SQL classes or database classes, you might recognize that the syntax here is wrong. There's an extra single quote at the end. So this should generate an error message from the form. So if I plug that in and hit the button, the form should fail. It should not be able to look up my email address. It should fail because of the syntax error in SQL. So that would be a good hint that whoever created this website is not protecting against a lot of these different types of attacks. So if I'm a smart attacker, my next thing I could try is just put some random value and close the quotation mark, put a semicolon, which means I'm done with that SQL statement. I'm starting a new SQL statement, update table, set email equals hacker@ymail.com. If that code were to execute just as it's written here, now notice everything in yellow is what I'm submitting in my form. So all that yellow text you see there is something as the attacker are things that I'm typing in to the into the input field, and when that gets executed, it's going to carry out those instructions, and it's going to essentially update every single email address in that table as hacker at ymail.com. So now all of the email addresses are effectively gone. So that's kind of a form of defacement, but I'm damaging their data, right? All of a sudden, all of their email addresses are going to change, which is, of course, a problem, right? If they're using them for authentication or to identify their customers and so forth and so on. So this is an example of a SQL injection attack. They're really not that difficult unless you protect against these. Then they can become significantly more difficult. And this is a great little cartoon from little comic strip online, XKCD, which is kind of a funny little technical sort of comic strip. But here, I'll let you go ahead and read that, and I'll stop talking for a second. So good old Bobby drop tables, right? And deletes all the student records because she gave her kid a name that's a SQL injection attack, right? Kind of a funny little comic strip. But that's the basic idea. All right, so the next one is an LDAP injection. Very similar to a SQL injection. Once again, we have a form. Maybe it's a web form. Doesn't have to be a web form. It could be a form in any application that I want to attack. Basically, I want to bypass the authentication from LDAP. If I understand LDAP and I know how LDAP works, and we're going to talk about how LDAP works a little bit in this class. So if I understand the protocol, just like SQL, I think a lot of you probably are very familiar with SQL because you've had to learn about it in a database class somewhere in either, whether you're a CST major or a security major or an informatics major, you probably had to learn a little bit about databases. And that syntax. Well, this is very similar. It has a syntax, just like database, SQL has a syntax. And if I understand that syntax, I know how to inject my own code, knowing that, I can kind of infer, what the rest of the code looks like, even though I can't see it. So in this example, username is what someone's filling out in a form somewhere. So if I put something else in there, so let's say I put BCG28, that should be querying the LDAP server for an account called BCG28, which is my Drexel ID. So that's a simple example. But what if instead I just put star? Well, in LDAP, the asterisk means just return all account names. So that would essentially find an account, even though I didn't give it a specific account. So a very simple example of an LDAP injection attack. But once again, if you're writing an application that uses LDAP for authentication, and you don't really understand the protocol that well. You're just kind of implementing some code, and you wouldn't realize that an attack like this would be successful. So it's really important to kind of understand if you're going to use these protocols, how they work, so you know what types of attacks might be successful. It's a relatively simple attack, but if you didn't know to catch that asterisk when you're sanitizing your input, then you would be susceptible to an attack like that. Another type of attack is XML injection. Let's say I wanted to use XML to do my user authentication in my application. So I might have on the back end somewhere an XML file that looks like this, which basically has different usernames and passwords in the XML file. Well, just like SQL, right? So SQL has a query language for querying a SQL database. XML also has a query language called XPath. And again, this is one of those things you probably didn't learn about in a lot of your classes, but it is very common. It exists everywhere. But XPath is the language for parsing and working with XML. So if someone's using that in their web-based application or in any application that has some way for us to provide input, if I know what those XPath queries are most likely going to look like, I can infer that because I understand the standard, then I can inject my own thing. So here we have a username and a password. This should work, right? So if I put in admin and my password, it should find that user account, user ID number 1. But what if in the user ID field, I put admin, close quotation mark, or 1 equals 1? Of course, 1 equals 1 is always going to be true, so that statement would return would return a record. It would return the admin account, even though I did not put the correct password in. Because of the Boolean logic there, because there's an OR there, with order of operations, it's going to do the OR first and so forth and so on. So this will still work even though I have a bad password. So I can bypass that check for the password using an injection attack. And again, it comes down to understanding the protocol and how it works, the programmer not catching or not sanitizing that input, and this type of attack will work every time if you don't sanitize that input. So that's an XML injection attack using XPath. One final injection attack, and this is a relatively simple example. Let's say you've got a website, and your website has, I think most websites, you have something like an index.html, which is, in this case, let's say I go to somewhere.com. When you go to somewhere.com, the web server is going to return the resource called index.html because it's been configured to do so. And maybe index.html has some photographs in it, and when you click on the link for the photographs, you can tell that that there's a folder called images, and inside that folder are some files like image1 and image2.jpg. So let's say that north of this directory structure, right? So you know that, okay, this server is probably a Unix server, for example, and you know that somewhere north of this is going to be some root. So for example, in some root directory, there's going to be some additional files. Well, what if, if I understand how to traverse through directories, what if I just put .. in the URL? Well, that should tell the web server to list all the files that are one directory up from where I am right now. So right now I'm in public.html. That's where index.htm is. That's where I land when I go to this website. But if I put .. it puts me into some root, right? So now I'm outside public HTML, and I can see a top secret directory. And inside that top secret directory, so let's say, okay, I can see this directory now because the web server listed directories for me. Now I know I can go into top secret, and I see that there's a file in there called passwords.txt. And now as the attacker, I throw passwords.txt on the end, and I can see the list of passwords. Game over, right? So I just found this file that was sort of outside that directory tree. Now, one thing you might say is, Brian, what about permissions? Obviously, they're going to have permissions set up so that only certain users can access this password.txt file. But under whose permissions does the web server run? Most likelihood, the web server probably runs under some privileged account that has access to files, because maybe it has to go and read that passwords file to authenticate users to the website, for example. So, by using directory transversal, I might be able to bypass those controls. Now, the reality is most web servers today would protect against this type of attack. Things like Apache and IIS, they definitely would detect an attack like this, wouldn't allow this to happen. But What if I had a homegrown application that had some integrated web server? This is something I could test for and make sure it doesn't work. Or, this could be something that could happen even within that public HTML folder. So maybe within public HTML, I've got 5 different websites, and within one of those websites, there's private information I don't want anyone being able to access. But if somebody is on a different website, does the dot dot trick and gets out of that and gets back down into another directory, because maybe through some reconnaissance they figured out that they're sharing the same web server, they might be able to access those files and folders. So we certainly want to understand that this type of attack can happen and to protect against it. And this doesn't just work with the web. This can work in many different technologies. So this can work in more than just websites. Pretty much anything that allows you to put paths into some standard format. All right, so those were just a couple of different types of injection attacks. Let's talk about the buffer overflow attacks. It kind of looks like it's the comb attack there, right? That looks like a comb in the picture. But what that picture actually represents is memory addresses. So each one of those little buckets that you see on the screen, those little blue buckets, would hold basically some bits, right? So each one of those would be a bit. Now this would be a very small amount of memory that we're looking at here, right? This is not very big, but this is just to demonstrate the concept. So let's say program A is in runtime, and program A needs to write 16 bits to memory. So it's going to go ahead and ask for 16 bits of memory, and it's going to get usage of 16 bits of memory. And then program number 2 comes along, and it needs 24 bits of memory. So it's going to get allocated 24 bits, and it's going to start using that 24 bits of memory to store variables and so forth in runtime. Now, there's 2 different types of memory, or really not 2 different types of memory, but 2 different ways to use memory. Some memory is executable or executed memory, and some memory is just for variables where it's non-executable. Some of you may be familiar with DEP in Microsoft Windows, which is basically execution prevention, which is to help prevent these types of attacks. But basically, you've got 2 different things in memory here, and there's really nothing guarding between these 2 different areas of memory, right? Program A has 16 bits. Program number 2 came along, and it got the next 24 bits of memory. And maybe program number 2 stored some stuff in memory, and maybe that stuff is going to get executed because program 2 is using the memory to execute some instructions in the microprocessor. Program A, in this case, maybe stored some binary data, maybe the number 39,321, which would look like that in binary. So it stored some binary data. Now, if I'm program A and I want something to execute, and I don't have, now here's what might happen is program number 2 might be a program that's running with elevated privileges. And I want some program code to run with elevated privileges. Now here's the thing. I don't need, if I'm an attacker, I only need program 2 to run just enough code for me to get access to something else that I need to then get full control of whatever it is that I want to do. So I don't have to do a whole lot with program 2. I don't need program 2 to do a lot for me, just enough for me to do something very small so that I can start to kind of work my way into this system to do something, for example. A lot of times I look at these attacks like a knit sweater. I don't know if you ever wear a knit sweater, but if you ever get a very small hole in a knit sweater, you can kind of stick your finger on that hole, and if you work your finger around, your finger will eventually go through the hole, and if you keep working around your finger, you can eventually get your whole arm through the hole in a knit sweater, right? Because the threads all kind of separate and move apart. And that's what I'm doing here. Program number 2 is that really small hole in a knit sweater. I just need to get the very tip of my finger into that little knit hole and just twist it around a little bit and keep going until I can get my whole arm through and practically walk through a knit sweater. So I've got my initial, in my 16 bits, I've got some data that I can stuff in there. But then let's say I know that I want to get 13,107. I need to get the binary equivalent of that into program number 2 to execute that, and that's going to cause something to happen that's beneficial for me. So there's 13,107. I simply concatenate that to what I'm going to store in my memory, and I try to store the whole thing. Now look what happens here. When I try to store that whole thing, notice that it overflows into the next program's buffer. So, and a lot of computers, a lot of subsystems in operating systems and so forth, they don't really have a way to control this. I asked for 16 bits. The assumption is I'm only going to use that 16 bits, but if I have some kind of programming code problem where I use more than that allocated than what I've asked for, it overflows into somebody else's memory. Now, normally, if I overflow into somebody else's memory space, it would crash their program. It would blue screen the computer, whatever. Something bad would happen. But I've carefully crafted this attack because I know what's going to be in their memory space based on, some reconnaissance that I've done. I know how that program works, so I know exactly how to craft what I'm storing in their memory space by using the buffer overflow to get it to execute some different programming, some different program code than what they intended. So that's basically what happens here. So it's going to basically execute what's in their memory space, and I've just kind of shoved that stuff in there without them knowing about it. That's basically how a buffer overflow attack works. Not a difficult attack in the sense of how it works, but it is difficult to plan this type of attack because you really have to understand how these different programs work. But this is definitely a powerful technique to get other programs to execute your code for you. A zero-day attack, a little less technical here, but the idea is that we can take any newly discovered vulnerability that has not been yet addressed by some kind of a patch, and from the time of the discovery until a patch is provided, we can use these vulnerabilities, which are known as zero-day. A lot of times, zero-day attacks are attacks that people have discovered that haven't been disclosed yet, or sometimes they're purchased online between attackers on the dark net and things like that, where they say, basically, to the highest bidder, here's a vulnerability in Adobe Acrobat or something like that, and then people buy it and then launch some kind of an attack until people figure out, how it works, and somebody like Adobe puts out a patch to prevent that type of attack. Most of the vulnerabilities that we hear about in applications are zero-day until there's some kind of a patch that prevents or fixes that type of attack. And a lot of times, vendors will not release information about vulnerabilities until they have a patch because they don't want it to be common knowledge until they have a way to fix it. So a lot of times they kind of keep it under wraps until they have some way to fix that type of attack. So cookies are basically small chunks of data stored in browser cache. Without cookies, you wouldn't be able to have state on the web. The web is inherently stateless, and without cookies, we don't have that concept of being able to log into a website. So if there weren't these things called cookies, we wouldn't be able to log into a website. So they're very important for a variety of reasons, but they can also be used against us. That's why if you go online right now and search for hotels at Disney World, I guarantee you for the next month, you're going to see Disney World vacation stuff in every website you go to, even if it has nothing to do with Disney, because they're very good at this sort of cross-site promotional stuff. And, they use cookies to track what you're doing on the web and to track who you are and to to drive the advertising to you. So if you want to see an example of cookies working, that's a great way to do it. Just search for Disney hotels and see what happens. But cookies can be used against us. We should remove them if we suspect that the cookies are illegitimate or if they're a part of some sort of attack. And likewise, cookies are really one category of locally shared objects. So these are pieces of information that's stored on the user's computer to save information from some application. Examples could be flat files, cookies, temp files, and so forth and so on. And they can contain private information. Those settings can be jacked or hijacked. We should remove LSOs when we suspect them, and we should try to avoid using applications that use LSOs when they should be secure applications. One of my favorite examples of this is a lot of these encrypted messaging platforms, for example. They kind of lull users into this false sense of security because they encrypt everything end to end, which is great, but they store all of your messages on your phone unencrypted, right? That's a locally shared object. And you don't realize. Now, a lot of those applications, you can turn on that encryption, but a lot of people don't because it's not convenient to do so. And of course, there's nothing that says somebody couldn't force you to unencrypt it, which could be a problem as well. So that's another example. And finally, malicious add-ons. These are pieces of code that are designed to add functionality to an existing program. They're most common in web browsers. So I'm sure that all of you have web browsers that allow add-ons like Chrome and Firefox, and I think even Edge allows some add-ons. But those add-ons could be malware, which we've discussed previously. So this is another avenue of attack with applications, is to create add-ons for an application that allows the attacker to take control of that application or do something malicious with that application. So it's just another type of application attack. All right. So finally, I have one more to add on here that I forgot about, which is transitive access, or transitive access, my apologies. And basically the concept here is that if A trusts B and C trusts B, right? So if B trusts A and C trusts B, then implicitly C trusts A through B, right? It's kind of like if you're going to buy a car and you go on Facebook and you say to your friends, what's a good place to buy a car? And one of your friends says, hey, my Uncle Fred works over at Sam's Used Cars. So you say, okay, well, I'm going to trust Sam because my friend Fred is related to Sam, right? Now, Sam could be a scumbag for all we know, but we trust that Sam's going to give us a good deal because we're friends with Fred. And why would Fred send us there if he didn't trust his cousin Sam or something like that? So transitive access is basically taking advantage of the trust between different applications to get from one place to another. Here's an example of doing this. And this is actually a famous attack used this technique more or less. Let's say I am a vendor and I have a VPN from my office into another vendor, into another company. So let's say I am a vendor that works with Target, for example, a large chain of retailers, and I have a VPN into Target and have unfettered access to many of the resources. And why do I have that? Because Target trusts me as a vendor, right? So I might be a vendor that Target trusts, and they, for a business reason, it makes sense for them to give me access to a lot of their resources. So we have this, this communication, this tunnel between our different systems, which we'll talk about how VPNs work later on in this course, if you haven't already had courses about VPNs. But then let's say an attacker is trying to attack Target. Target has really good IT security. It's very difficult to attack Target. They're very good at what they do. They've got a good, strong IT security team. They know what they're doing. They've got all the right controls in place. They're protecting against all these attacks. But then that vendor that we were talking about, let's say that vendor is an HVAC company, for example, and their primary business is heating, ventilation, and air conditioning systems. And they happen to do a lot of business with Target, which is why they have this VPN, so they can monitor, let's say they're monitoring HVAC subsystems in these different locations for Target. And their core business is in IT. They got a couple part-time IT guys. That's about it. IT security is sort of a second, a second thing for them. They don't really care about it that much. So they don't have a lot of controls in place. So if I'm a smart attacker and I know that, instead of attacking Target directly, instead, I'm going to target their partner. I'm going to target this vendor that Target uses because I know it's going to be a whole lot easier to get access to their network. Once I get into their network and once I have access to their systems and applications, because they trust those applications, then transitively they're going to trust my malicious code because it's coming from that vendor. So that's an example of how transitive access works. So it's important to know who you trust. All right, so that concludes some different attack methods, and we're going to talk a little bit more about attacks in the next week. So in the next unit, we're going to revisit some of these attacks and some different ways to protect against these different attacks and vulnerabilities.